All right, guys, so this is the 2.3 lesson, which is describing how to solve kinematics problems. So we've measured several different ideas at this point. So just to review them, the quantities that we use to describe motion include acceleration, which is the symbol for that is A here. Then the unit for it is positive or negative meters per second squared. Again, positive or negative is only the direction. It does not mean anything else. Then we have initial velocity, which would be VI, so the velocity at the beginning of a time interval. And again, positive or negative for a direction, meters per second, this time for the units. Final velocity, which is the velocity at the end of a time interval. It doesn't mean it has to be at the very end of the motion. It can be during the motion, just like the end of a time period. So final is a little bit misleading, but again, same units as initial velocity, positive or negative for direction, meters per second. We also discussed displacement, which is just how quickly an object, or I'm sorry, how far an object changes its position in a positive or negative direction, and that's in meters. And then we also have change in time. Time is the only one that doesn't have a positive or negative associated with it. So that's the scalar quantity, and everything else is a vector. So instead of working with graphs all the time, you're not always going to be given a graph or data for a graph or a motion map. Sometimes you'll just be given a problem. So we need to come up with a strategy to solve these types of problems. So these are 4 equations that we're going to use, and they look kind of complicated in the beginning, but they will be easier as we work with them. That you'll be more familiar with them. These equations are the 4 equations we're going to use. And these equations only work if you have what's called a constant acceleration. So we don't always have constant acceleration in everyday life, but in these problems that we're going to consider, we will always kind of simplify it down to that the acceleration is constant and unchanging in the time period. If you didn't have constant acceleration problems, you would need calculus to do that work, and this is not a calculus-based class. So, so these equations have those variables. So the variables we just had on this previous screen here, they are just represented by their symbol, and the equation itself relates how they're related are. So for the first one, VF equals VI plus AT, it is relating final velocity, initial velocity, acceleration, and time. Now, every problem is not going to have you solve for final velocity. Sometimes you might have to solve for initial velocity, acceleration, or time. So you might have to do a little bit of algebra and rearrange these equations. But generally, I tell people to plug in the numbers and then try to do the algebra. So these 4 equations I usually number with 1, 2, and 3, and 4, and I'm going to have them there so that when we I'll ask some questions about which equation do you think you should use, and hopefully you'll pick the right one. This column over here is going to lead you to decide which equation of these 4 would you want to use. And it says not given, so I'll come back and explain that in a second. So here are the general steps, 4-step process to solve these kinematics problems. So the first thing, you're going to read the problem, and then you're going to draw a sketch. So you just draw a picture. It doesn't have to be fancy artwork. It can just be a dot to represent the object, and then arrows to represent how the motion is changing. You're going to list your givens in a table. I'll show you how to do that. You're going to determine which equation to use, and this is usually the hardest step. So between listing your givens in a table, step 2, and step 3, those are the ones that give some difficulty to people. Once you get those done, then it's really just plugging in and doing math. So I think you're going to do fine once you get to that point. Okay, and then you look at your answer, make sure it seems somewhat reasonable for the situation. So we're going to practice just by starting out with a situation like this one, where it says a car is moving at 20 meters per second, and then it hits the brakes and undergoes an acceleration of -4 meters per second for 2.5 seconds. So the first thing I want to do is just draw a quick sketch. So I'm going to draw a car. So there is a car. And it says the car is moving at 20 meters per second. So it's moving in the beginning, so I got an arrow. And then it doesn't say it's going to the right, or it doesn't say it's going to the left, but I'm going to assume this is positive because it didn't say that it was negative. So it hits the brake and undergoes an acceleration of -4 meters per second squared. When you hit the brakes, typically what happens to your car, if it's working properly, is you slow down. So I'm going to make this arrow get smaller. So as you can see, as I draw this, the arrow in the beginning is starting big, and then it's getting smaller and smaller. This is a good enough sketch for what we need. You're going to draw a picture similar to this in most of your problems with whatever the object is. Again, you could just put a dot. There's nothing wrong with just having a dot, that is fine as well. So so that's what we got so far, and I've underlined all the numbers now. So positive 20 meters per second, negative 4 meters per second squared, and 2.5 seconds. We are looking for the car's final velocity, so that is what it's asking us to find in this problem. So we've done step 1 out of our 4-step process, which is to draw a picture. The next thing we need to do is list the givens in a table. So I just make a quick table like this over to the side, and I write in the 5 variables that we have in these problems. So I have displacement, delta x, initial velocity, vi, final velocity, which is vf, a for acceleration, and our change in time or time duration, which is t. So we're going to take the information in this problem and put them in the chart. So I need to go through and kind of figure out what's what. So positive 20 meters per second. Meters per second is a unit for velocity. So I know this is a velocity, and I need to decide if it's the initial velocity or the final velocity. So it's moving at 20 meters per second, and then they hit the brakes. So I think it's going to change from 20 meters per second to some other number. So I'm going to write 20 in for the initial. So 20 and meters per second. And that's a positive value. Hits the brake, undergoes an acceleration of. So acceleration of, that's a good indicator that this is negative 4 for A. And it's meters per second squared. So meters per second squared is the unit for acceleration. So if, again, we go back to this slide, you can see meters per second squared tells us an acceleration. So just by knowing the unit, I know where that fits. Finally, 2.5 seconds, that's the time. So I'm going to write 2.5 there. Okay. Just to be clear, we have 3 out of 5 possible variables. So if you have 3 out of the 5, you are good to go. You are ready to solve for whatever you need to solve for. So we need to just figure out what we're looking for. We're looking for the final velocity. So I'm going to put a question mark here in final velocity. So this is really important. We have our table set up. We have our 3 variables that we know out of our 5, and we have our question mark, which is what we're looking for in our question. So it's like the goal, the aim of the question is to solve for that quantity. So now I'm going to get back to this kind of table with all the equations. You can look for the equation that has all 4 variables that you want in the relationship, but that's harder to do. So like you have to look for 4 things here. If you check this out, this thing is the thing that is not involved or not given. So if you come back to this table and you say, okay, delta x is the thing that was not given, there is no delta x in that equation. That means all the 4 other variables are there. That is the one that I want. So I'm going to use that equation. So I'm going to just take a picture of it because it's easier than me. Sorry, capture tool. That's what I want. Where'd it go? Oh, it just showed up. There it is. Okay. Let me just do something real quick so I don't lose it. All right, so I'm going to just take a picture of that equation, and I'm going to send it to this page, and I'm going to use that equation. So I have that equation all set up to use, and I'm going to solve. So I'm going to plug in, and I'm going to type out my expression, just because typing is probably better for you guys to read it. So it's VF, sorry if there's a little subscript errors or whatever, but VF equals 20 plus, plus negative 4 times 2.5. So just to be clear, I don't need you to write in the units when you're plugging in for the math. Sometimes that confuses people. I generally tell people just to put it in their equation that way, and then do the math and solve. So negative 4 times 2.5 is negative 10, so it'd be 20 plus a negative 10, which is going to give you 10 meters per second. It's a positive value because the car is still moving to the right. And that should make sense. So it slowed down. It went from 20 to 10 meters per second in that amount of time. So that is simply what you have to do. So it's just doing a little bit of algebra once you have it set up. Now this equation was pretty easy to use because it was already set up for VF. Some of them are a little trickier, but that's okay. So I could take that answer of 10 meters per second, and I could put it in here if I wanted to, and I could fill in this box, and instead of having a question mark there, I could now put in 10 meters per second as positive. Okay, so we've gotten our fourth box, so now we have 4 out of the 5. If you have 4 out of the 5, you're in really good shape, because then you can pick whatever equation you like as long as it has the variable that you're looking for. So in example 2, it's the same problem, but this time it asks for how far did the car travel. How far is a measurement of displacement. So we're looking for how far did it change its position. That's delta x. So we can go back to this equation sheet, and we can figure out whatever equation we want to select, and that's fine. So I would recommend picking the one that looks the simplest. So we've already used equation 1, so it's not going to be that one. So it's either equation 2, 3, or 4. So let me give you a second to consider which one. I would pick equation 4 because it looks the easiest to me. This one has t and t squared, so that kind of looks weird. 3, it's not set up to solve for x, so I'd have to do algebra and move that around. This one just looks like it's pretty basic, so I'm going to use that one. And I'm going to use the screen capture tool again to take a picture of that equation and use it. All right, so moving that down and shrinking it a little bit. So we're going to use that equation to solve for the displacement. So if I plug in the numbers here, okay. So I'm looking for delta x. So I'm going to draw a triangle next to the x because I don't have a triangle symbol handy. So triangle x, or delta x, equals 1/2 the initial velocity, which was 20, plus the final velocity, which was 10, and I'm going to multiply that. I'm going to multiply that by 2.5 seconds. So oops, that should be a dot, not a comma, unless we're in Europe somewhere. So if you do that math, 20 plus 10 is 30, half of 30 is 15, and then 15 times 2.5 would be 37.5, and it's going to be meters. And it's a positive value, so that makes sense. It's positive because all the velocities are positive, so this car is moving to the right like we described it. So if we look at this, the change in position from when it's going to 20 until it goes to 10 meters per second, and that 2.5 seconds is this value. So hopefully that isn't too bad, and that's just some examples of how to do that and work with these kind of problems. So let's try another one, and we will pause there and get into free fall after that. So let's try this one. So again, if you have your notes printed out, or if you have a piece of scrap paper, I would start working on this problem. So it says a car starts from rest, accelerates at 3.5 meters per second squared. How far has the car moved when it's traveling at 25 meters per second? And then how much time has passed? So again, starting with our picture, so we have a car. I always draw the same kind of boxy car with that. And it says it starts from rest. It accelerates at 3.5 meters per second. We want to know how far has the car moved when it is traveling at 25 meters per second. So I'm going to write the word rest, because that is an important word. So it has a meaning. If you're at rest, what does that mean? It means you're stopped, your velocity is equal to 0. So we're stopped. So I just got my dot there for the car, if you want to do a motion map kind of thing. And then it's going to accelerate. So it's got a positive acceleration. If it's not moving and has a positive acceleration, it's going to start moving to the right. And it's going to increase its velocity. So there you go. I drew a couple arrows. That's good enough for a sketch of the ideas. So next thing is setting up our table. Again, it's just the same 5 variables: delta x, vi, df, a, and t. So filling in these things, it starts from rest, so that's the initial. So vi is going to be 0. Again, velocity is meters per second. Accelerates at 3.5 meters per second squared. EF is going to be 25. because it's the velocity at the end of the time period. And that's it. We got 3 out of 5. We're good to start solving. What's interesting about this, in part A or part B, it doesn't really matter which one you do first. So in part A, it says how far has the car moved. So we're looking for this in part A. In part B, we're looking for how much time. It does not make a difference. You could solve for A first and then use that answer to get B. You could solve for B first and use that answer to get A. You could solve for each one without the other one. It doesn't make a difference, but I'm going to do it in the order that it was written just to make sure it's consistent with kind of what's here. So for part A, I need to figure out an equation that does not have time in it. So I'm going to go back to that equation page and say, okay, I need the equation of the time. That is this one, which is equation 3. So I'm going to take a picture of that and bring it to the slide. And this one's a little more complicated, but it'll be fine. We'll work through it. So that is the equation we're going to work with. So it's VF squared equals VI squared plus 2A delta X. Again, if you really don't like that equation, go to part B, do that one first, and then pick a different equation there. You don't need it. It is totally up to you. So for VF squared, that's going to be 25, and I'm going to write squared with the caret kind of math notation. 0 squared is going to plug in for initial velocity, plus 2, A is 3.5, and then we are looking for X or delta X. So I'll write in that, draw in that triangle again. Okay, so so this is not set up to solve for X right away. So we're going to do the math and plug in and then do some algebra. So continuing on with that. That delta is giving me trouble. There we go. 25 squared is 625. 0 squared is 0. 2 times 3.5 is 7. And then we have the triangle X again. So I'll again draw on a triangle here. So 0 just goes away. So it's 625 equals 7x. We're going to divide through by 7 on both sides. And you get delta X is equal to a positive value, and that delta X value is approximately 89.3. So you might get a slightly different number. It might be 89.2 something something something. I just round to the nearest decimal or 2 decimals. You don't need to go any further than like the hundredths place. So tenths, hundredths would be here. So, and the unit for displacement is meters. It's positive because all the values again are positive values up here for our final velocity. So that is the answer to part A. We could use that answer and solve for part B, but I don't think I'm going to even need that because I'm going to pick an easier equation for part B. So for part B, it says how much time has passed. So I'm going to act like I don't know the answer to A, even though we have it. It's that there. But I'm going to use the equation that doesn't have delta X. So going through that equation and looking for the one without delta X, it's the first equation. That's one of the easier ones. So we're gonna pick that one. You could try to solve for 2 or 4. It doesn't matter. You could do that. It's just you can't use 3 because it doesn't have time. So any of the other equations would work, but I'm going to use the first one. So taking a picture again of the equation. What I want you to do is to kind of follow these steps when you're writing out problems and you're solving problems, when you're doing tests. This is a model for what you should be doing. So like I try to make sure that you are showing the same amount of work. If you're showing significantly less work than me, I would say you might lose some points and you get partial credit. So you want to make sure that you are getting all the credit that you deserve. So I'm going to plug in numbers. So VF is our final velocity. That's 25. Our initial velocity was 0. Our acceleration was 3.5. And then the last thing that we're looking for is the time. That's what we're solving for. So I'm going to leave a space and write t. Whoops, I don't want to be there. I just want to draw on a triangle. So I got 25 equals 3.5t. I'm going to divide by 3.5 on both sides. Again, the 0 just goes away. You don't need to worry about it. 3.5. So if you divide 25 by 3.5, you get a time equal to, again, you can round 7.1, I said 7.14 seconds. So that is how much time it takes to go from 0 to 25. If you wanted to check this and just to kind of show you again the idea, the concept to make sure it checks out, we're looking at velocity as a function of time. Our initial velocity is 0 at time equal to 0. So let's just count. So if I have 1, our acceleration is 3.5. So our velocity after 1 second is going to be 3.5. We're just going to continually add 3.5. So that's going to be 7. 3 seconds, it's going to be about 10. So if we doubled that, and we did 4, 5, 6, oh, sorry, 10.5. Finally 7. So if I had 3.5, that's 14. 17.5. At 6 seconds, I'm at 21. At 7 seconds, I'd be 24.5. So we know it's just slightly after that is kind of when the 25 meters per second would occur. So again, it's just repeatedly adding that same change of velocity. So it's adding, again, that's what acceleration means. It's 3.5 meters per second. So again, just conceptually, for every second that goes by, we're adding 3.5. So we're just repeatedly adding 3.5, 3.5, 3.5, 3.5. Okay, so that's basically it. That's horizontal one-dimensional motion. The next lesson is on free fall, which is just basically taking that horizontal motion and making it go vertically. So there are a couple other subtle differences, but we'll get into that in the next video. So have a good one and be well.